All right. Hello, everyone. Thanks, everyone, for coming in person and joining online to the latest edition of Mython Times. Today, we have the pleasure of hosting Miroslav Lžičař, who is the current CTO and co-founder of Deep MedChem. I believe that previously he worked in R&D at Mama AI, and even before that, he was a Python developer at Charles University, where he studied bioinformatics and I think even before that, philosophy, right? He's a machine learning engineer who focuses still on bioinformatics and chem informatics, right? Today, he's going to talk about exactly that, about very large databases of molecules and how to quickly search through them, I believe. So yeah, Mirek, the floor is yours.
Yeah. Hello, everyone. Thanks for the introduction. My topic of this talk is called utilizing embeddings for drug discovery in billion-scale databases. We will soon start sharing the screen. Yeah, thanks. And today I would like to talk about some problems with state-of-the-art semantic search, how to overcome them, and how to use semantic search in some unconventional domains, such as chemistry, and how to make it scalable to achieve cost-effective semantic search even in billion-scale databases. I would like to directly follow up on the previous talk, which draw a distinction between lexical search and semantic search, where lexical search means search by terms and frequencies, which is based on exact matches or verbatim word similarities, and usually there are some sparse vectors or binary codes to represent the sentences or document which we are searching, while semantic search searches mainly for meaning, not for words. It uses AI-learned vector embeddings, which are dense vectors, and it is possible to support multiple modalities, not only language, but also images, sound, etc. So, but what about in chemistry? In chemistry, current searches of molecules work in this lexical way. They are using binary codes, so-called fingerprints, which are encoding some parts of molecules or their features. And the most similar molecules have, in this paradigm, the most exact matches of bits of those features. But semantic search is not currently available in chemistry, as at least some kind of semantic search which would be consistent, interpretable, and applicable also in clinical settings or in drug discovery. It's mainly because those dense vectors, which are AI learned, work on based on some intuition, let's say, and it's hard to tame them to return consistent results. They are being mocked as black boxes, and scientists cannot rely on them to have accurate results. And needless to say, this is not only a problem of applying semantic search in chemistry or in science, but also we have scenarios where we want higher factual similarity. We are searching for some facts, and there the semantic search is not performing very well. Here's an example of a current semantic search. If you search in Google the word wave and waving, it will, with high accuracy, identify like what's the meaning or what's the concept of the word, while only lexical search could be confused because those words are very similar. This is how semantic search works. In chemistry, as I said, there is this kind of lexical search where we are representing parts of molecule as binary bits in binary fingerprint, and then for searching the most similar, we are using some binary similarity, such as Tanimoto distance or Hamming distance or Jacquard index. Most commonly is, for instance, the Tanimoto distance, which is very related to Jacquard index, and that's an set similarity. Basically, it's an intersection over union, where if you have multiple of those binary fingerprints, you are searching how many bits do they have in common, divided all the bits they have. So now imagine that you are a medicinal chemist and you want to discover new drugs, for instance, some analogs of aspirin, which is a well-known molecule. But if you enter aspirin into Google search, you will get mostly some like products, which is where Google is really good at. But let's say you want to search for similar molecular graphs, similar molecules in the chemical sense. For that, it's good to know that you can represent molecule in a plethora of ways. You can represent it via the trivial name as aspirin, or as an image, or as some formula or graph, or even 3D shape, or some electrostatic surface or wave function. But for searching molecules, chemists are most commonly relying on the string notation, which is called SMILES. That stands for a simplified molecular line input enter system. And it is basically a string notation of the graph as described on that scheme. You don't have to like understand what does it represent, but you need to know that the string is exactly describing what is in the graph, and based on the SMILE string you can construct the original molecule. So that's some way how you can convert molecules into string sentences and process them using AI models. So now we have a better representation, and we are searching the notation of the aspirin molecule in Google. Yet those results, you don't have to understand chemistry to see that those results are not so convincing. We have a lot of totally unrelated molecules, and it doesn't have any sense if you are a chemist and you want to search similar molecules. And in this talk, I will show how to tame the AI to produce consistent results and go from this to something like this. This is cheese, which stands for chemical embeddings similarity engine. And if you search by the SMILES notation there, you will get, using semantic search, very similar molecules in the chemical sense, which you can try directly in your laboratory to see whether how do they compare to aspirin, and maybe patent them or try how efficient drugs they are. So once more, here is what you get with Google when the semantic search isn't forced to produce consistent results, and this you will get with some like conscious constraints on the latent space of those AI embeddings the model is learning. Topics of today's talk will be what's wrong with state-of-the-art semantic and lexical search, how to tame semantic AI models to ensure the interpretability and consistency of their results, how to design scalable vector databases with fraction of the cost, and why I think that semantic search, when used consciously, could revolutionize drug discovery. Let's contrast the lexical and semantic search now in the context of chemistry on some examples. So if you have semantic search, you are usually working with vectors which are respecting some Euclidean distances or cosine similarity, and you have neat Euclidean space with Cartesian coordinates, and you can to retrieve the most similar vectors, most similar items. It is sufficient to search for the closest vectors in the Euclidean distance sense. It's very simple, neat, efficient, and you can use a lot of algorithms on the top of that. In Euclidean space, you can do efficient clustering. You can easily search for some paths in the latent space, optimize something in there, and do very efficient approximations to search for the most similar vectors. Whereas with those binary fingerprints, let's now focus just on Hamming distance, because that's the most simple. With Tanimoto, it's like even more complicated. With Hamming distance of binary codes, you have some like Hamming hypercube, where basically one step or distance equal to 1 is when you change one bit. So to get from there to there, you need to change 2 bits, one step and second step. So the latent space of those binary codes is more complicated, and it's hard to implement like any algorithms or efficient approximations on the top of that to do more stuff. Specifically, with binary fingerprints in chemistry, to search the most similar molecule with the Tanimoto similarity, you need to compare the binary code with all the binary codes in the database. So it has linear complexity, and if you increase the size of the database twice, you need to do twice as many distance comparisons to retrieve the most similar binary codes. But with vector search in Euclidean space, you can try some tricks. For instance, searching just the nearest cluster of molecules. So you will do only square root of the distance computations, and then take the cluster and search the most similar vectors in that cluster. So this way you can get from linear complexity to square root complexity. It will be non-exhaustive, but it will guarantee you still to get the most similar vectors. So what are the problems with current approach employing binary codes in chemistry? There are multiple. One is that it's kind of bag of features representation. Some chemists invented that those parts of molecule will be ones and another parts will be zeros, and it's kind of like handmade, and thus it's inflexible because there are much more sophisticated chemical similarities, for instance, similarities in some properties, or shape similarity, or electrostatic similarity. And for that, it's virtually impossible to design some binary codes of parts of the molecule to capture the metric reliably. Then it's also inefficient in the Hamming space. It's much more difficult to do some vector operations, such as k-means clustering. It has thus limited scalability, and at best you can achieve linear complexity. It's also slow. You need to forget about billion scale databases, because with these linear comparisons, very quickly it will be slow, taking hours, days, or even weeks to perform single search. One example of what you cannot achieve with those binary fingerprints is a shape similarity search. This is a super relevant metric in evaluating protein-ligand interactions, because to find a successful drug, to find effective drug, you need to find a molecule of the right shape. The molecule fits into the protein as a key into a lock. And if you find such a molecule of the right shape, it will have much higher rate of inhibition, thus being more effective drug with less severe side effects. But how can you encode shape with binary codes? That's very difficult, and you would need to disassemble the shape of the fuzzy shape of the molecule into some parts, define which are ones or zeros. It's virtually impossible. But with AI learned embeddings, you can compute the shape similarities and make the AI model to learn such vectors which would respect the shape similarity or the shape distance of those molecules. So the main selling point is that it's way more flexible and machine trainable. Here is some example. We are now searching for shape-similar molecules, and with binary fingerprints, you will get results such as these. But with cheese learned on 3D shape similarity, you will get much more shape-similar scaffolds of molecules. Once more. But a semantic search is not foolproof, and it has its own problems and challenges. Mainly, the vanilla semantic search doesn't guarantee you any specific distances of the vectors, so it learns some latent space which might lack interpretability and be prone to some biases or inconsistencies, because you cannot guarantee where are those vectors, how they are exactly related, what's the distance between them. So it on a biased data set, it will learn some biased distances of those embeddings in the latent space. then the accuracy is good in some fuzzy sense or some intuitive sense, but it has many drawbacks if you take more factual data set where you are searching not only for meaning, but also you are providing some facts and want the semantic search to be accurate. And finally, the costs and scalability, we will see. I have a good example for that, but it's really not scalable if you have billion scale databases. It's virtually impossible with current vector database providers and technologies. The applicability is also limited. It works on so-called unstructured data, such as images, sounds, or NLP, but it doesn't work with structured data or some more exact data or some data you would like to use in science. And are the latest large language models really more accurate than lexical search? Well, not at all, not in all context, especially not in some factual in-context retrieval. There are multiple papers on that. For instance, in this paper, they have a benchmark where they are comparing GPTs, BERTs, and with basic BM25, and it often performs better. BM25, that's just a lexical search. It often performs better on those factual data sets, and it's also way more cost effective because you don't have to compute embeddings with the large costly language model, but you only need to assemble those frequency-based sparse vectors. And what's the price? So we had a use case in Deep MedChem. We had and we computed that for 1 billion vectors with these commercial providers, we would need around 2 terabytes of RAM on some cloud instances and pay for it around for $3,000 per month for the size of database of 1 billion. But in fact, for some practical chemical databases in chemistry commonly is used an real database which has 5 billion molecules, and we have four indexes for similarity metrics, and so that's in total $60,000 per month, as we got like quote from one of these commercial providers. Now let's get to those solutions we employ in Deep MedChem. So far, I've talked about multiple problems, but what can we do about it? First of all, let's tackle the issue of accuracy and consistency of those vector representations. In the semantic search, usually you are training some kind of networks, such as triplet neural networks or Siamese neural networks. Here is example on images, and it works in following way. In the training data set, you have multiple triplets where there is always some positive example, some negative example, and in case of triplet networks, there is some anchor, and you are optimizing the vector distances for the positive example and the anchor to be closest, and you are penalizing it, penalizing the distance to the negative example. And in this way, the latent space after the training will be clustered in such a way that those images in similar class or sentences which are semantically related will be close together, but those interclasses distances relations will be distance, and there will be space between those clusters of multiple classes. That's one way how you can train it, but there are of course multiple models and multiple ways how to train model for a semantic search. The difference with metric learning, which is a method we use in Deep MedChem, is that in the case of metric learning, you are not providing positive and negative examples, but you can specify the exact distances of the vectors. So you always have two items. Let's say you have two molecules, and by some measure they are similar, like 0.5 similar. So you can train the model in such a way that a pair of molecules which is 0.5 similar will be penalized to get the Euclidean distance of those high-dimensional vectors to be exactly 0.5. For 8.5 and for 0.8 similar molecules, you will get the distance of 0.8, and you can force the AI model to learn exactly the distances which you want, thus making the latent space much more consistent, and having some guarantees on how it will look like, and that it will be respecting some relevant metrics which you want to train the model on. Here is an example. For instance, we trained a model on molecular shape similarity, and you can train it in such a way that you will pass those molecules into the AI model, and then the loss function will be if those AI learned vectors are respecting the original distances. So in this example, those two molecules do have 0.9 shape similarity. They are very shape similar, so that stands for 0.1 Euclidean distance. So the AI will learn some embeddings, some vectors, which will be forced to have 0.1 distance. They will be very close together, and then if you search one of these molecules, you will have, with a high probability get the other as the closest vector. And now, what about the efficiency? So we have consistent latent spaces with neat embeddings, respecting some the metric we want, and having the proper guarantees. Now, how to make the vector database billion scale? How to make it efficient? This is maybe it's kind of problem of this application, because in language, if you are not Google, you have usually smaller databases, but in chemistry, billion scale or even trillion scale databases are really commonplace, and current vector databases are not prepared for that. The first thing you can do is to construct the so-called inverted file index, which means that first of all you will do a clustering on the latent space of embeddings, and it will be clustered into these Voronoi cells, let's say, or it depends on the if you use k-means algorithm or some different algorithm, and then you will have sub-indices for these clusters, and while searching, you will search for the closest centroid, then take this sub-index and search in the sub-index for the closest vectors. That's one very successful method how to scale it up. Another method is so-called product quantization, which is a technique of converting dense continuous vectors into integer codes. And it's kind of a trick where you take the original vector, you divide it into linear subspaces of the number of subquantizers that you want, and in all of these subspaces you will perform a simple k-means clustering, and for each cluster you will have some integer. And then you can take take the vector, and for each part of the vector, for a very, let's say, 16 dimensions, assign it the cluster in there, and then it will be converted into much more efficient representations. Why? It is because with dense vector you have usually some floating points, 32 bits or 64 bits, but here with PQ codes you will get much smaller code, and you will also get int 8, so 8 bits for each dimension. So that's 100 times. Or here in this particular example, it's like 64 times reduction in memory. Here on the top, there is an illustration how it looks. There are actually multiple methods, not only product quantization, but iterative product quantization or optimal product quantization. There's a whole field about it. What's important that it compresses the embeddings a lot. You can have at least 60 times lower memory footprint, and search much more, search with much higher speed, and so on. So it has many advantages, and actually it's very accurate, and you can tune the accuracy by the number of those linear subspaces to which you will divide the original vector. Specifically in cheese, we use a combination of those two methods, both inverted clustered indexes and product quantization. And using that, we achieve around 100 less memory. We also achieve the square root complexity of the search, much higher speed. On those billion scale databases, we can search in seconds. And in contrast to contemporary vector databases, that's our trade secret, we are not performing the operations in memory, but on disk. So we need only disk and CPU, and we are not, we don't need 2 terabytes of memory, which is very expensive, but only hundreds of gigabytes of disk. And for the previous example, where for the NMN database, the cost of using some contemporary vector database provider was around 60,000 USD per month. With our solution, the costs are estimated to be around 200 USD per month. And now we have efficient, scalable, and accurate search. And why to do that? What are the applications specific for drug discovery? To introduce the process of drug discovery, I need to say that primarily it's slow and it's costly. For one drug, it takes around 5 to 10 years and around 2 to 3 billion USD to develop the drug and take it from the first screening to the final phases of clinical validation. There are also exponentially growing chemical databases reaching billion and trillion scale. Existing algorithms such as the binary codes like the quality and chemical accuracy to satisfy all the use cases and in clinical drug discovery. And only a negligible fraction of highly potent compounds can be found. In drug discovery, we are searching needles in a haystack. And with better search, we will find more needles, and thus it will be possible to test more molecules, iterate more quickly, find more potent molecules, and discover more drugs in for a fraction of the cost in less time. Some applications on this drug discovery procedure are not only this scalable semantic search, but also we can use the latent space of those AI learned vectors in another ways. One way which is particularly interesting is ultra-fast property prediction. Molecules have a lot of properties, and for instance, drugs have some side effects, some toxicities, some properties of bioavailability, properties of the distribution or clearance, or there are many properties of drugs. And with some mathematical representation of molecules, we can predict those properties, and we can predict them very efficiently if we have efficient latent space. Then there is also possible to cluster really large databases, thus making everything else more efficient. It's also possible to use it for visualization, and finally, in almost all the steps of the virtual screening that's needed in drug discovery. There are as well opportunities that we are now researching. One opportunity is, for instance, to use the multimodality property of semantic search and to embed not only molecules, but also the targets, the proteins, and then search for instance, the best molecule, the best ligand for some target, or vice versa. There is also an opportunity in combinatorial databases, because some I will show it on the next slide. Some databases are not enumerative, but are combinatorial. There are some building blocks and reactions specified, and then the database is considered as a product of all possible chemical building blocks by the means of all the possible specified reactions. I will show it. Here, this is an example of the prediction in this cheese latent space. We have a database of 5.5 billion molecules, or 5.5 billion vector embeddings. And since we can perform efficient clustering, we can convert it into 70,000 cluster centroids. How to obtain cluster centroid? You can just take a mean average of some molecules which are similar, and you will have good centroid of that cluster. And then you can predict properties on those clustered centroids. And that's possible to do in few seconds. Here in this example, it takes us like 10 seconds. And in this way, you will, if you are searching, let's say, the most active molecules or the most effective drugs, you will need only 10 seconds to approximately search in this super large database. And you will have very good approximate predictions. In contrast with some competitors or traditional methods, it would take from 7 to 100 days to be able to make this prediction. Yeah, this is illustration of the combinatorial search. It's what are these databases? Here you have on the x-axis multiple chemical databases from the smallest to the biggest, and the biggest ones are in billions, trillions, or even more. Specifically, the largest ones are so-called combinatorial, which means that you have some building blocks, and then you are combining them. And to specify the database, there is some combinatorial definition of the possibilities of the combinations or of the synthesis path to obtain all the resulting possible molecules in the space of the possibilities of chemical synthesis of the products that you have. And we are researching ways how to tackle this problem in the vector space efficiently too. We are experimenting with some formulations such as vector reachability problem, which is a problem famous in mathematics where you have some vector and you are trying and evaluating whether it can be reached with another vectors. And in this way, you could basically make the combinatorial synthesis as a very efficient operation in the vector space. Another example is the macro level. Here is a protein, and we train the model which is utilizing embeddings of proteins on the atom level, and it is, for instance, possible to fold proteins in this way. So this is our prototype, which we call cheese fold. Maybe you know AlphaFold, so this is something similar to that. And on the macro level, you can use embeddings, for instance, for representing electrostatics and making some quantum mechanical computations much more efficient. In this example, to compute partial charges for this molecule, it would take 30 minutes or even hours to compute that with quantum mechanics, but using some embeddings and consciously employing AI techniques, you can predict that in a fraction of a second and get a high correlation with the proper DFT quantum mechanical calculations. That's all. Thank you for your attention.
Right. Thank you, Mirek, for the great talk. Now is the time for questions. If you're in the room, I will pass you the mic. If you're online, please just unmute yourself. We should be able to hear you. But we have already one question in the room, so.
Okay, thank you for the talk. I got 2 questions. So one would be, you mentioned that you're using smiles as an input representation. I wonder, how do you tokenize it, represent it, and encode it for the final embedding? So that would be first question, and ask.
Thanks. The question is, how are those smiles tokenized? it's actually tricky. It's actually very tricky because you can employ some character level tokenization or byte pair tokenizations, but those techniques usually do fail very much because there's a problem that if you change one character, let's say parenthesis, something somewhere in the middle, it will be a totally different molecule. It can change really much, and if you intermingle some characters or tokenize it quite differently, it will be a different molecule, and it's very tricky. And for instance, that's also a reason why a lot of generative models are struggling a lot. If you go to GPT-4 and you will tell it to generate some molecules in Smile's definition, it will usually output some like garbage and nonsense, because the tokenization that's really a problem here. And we have some techniques for that, but that's a trade secret.
Okay, so I understand why it wasn't in the presentation now. And the second question was that you mentioned that you can have multiple similarities between the molecules, and you mentioned only the shape similarity. So do I understand correctly, the model is only trained on shape similarity, or it trains on multitask of different similarities? And if it is, can you search given a weight of specific similarity?
Yeah. Yes. Thanks for this question. The question was whether there are also multiple similarities, not only shape. The answer is yes. I was demonstrating it on shape similarity, but on the Cheese webpage, if you go to cheese.themamaai.com, you will see we have there also electrostatic similarity, or another kinds of similarities, shape and electrostatic combined, or in the latest version, we have also activity similarity, or a similarity in the way whether the molecule is similarly active or like similarly good drug.
Great, thank you. So, any more questions? Yeah.
Yeah, thanks. I just want to nitpick first that aspirin is actually not the generic name; it's acetyl salicylic acid. So but because it's such an old drug, then people use aspirin interchangeably. So it might not be the best example. But anyway, I wanted to ask about the. You are comparing basically the lexical search with fingerprints versus the semantic search with embeddings. And you are saying that you can use tricks, including clustering, to improve the search efficiency and stuff like that. And I think that you could also do that with the lexical search. There are many ways how to cluster molecules without embeddings, and then you could potentially kind of like identify the most similar cluster and then search only within that cluster. So I'm wondering whether there's something inherently better, or you are like comparing this brute force approach, searching all of the molecules and then comparing it to your clustering method, which was obviously fast. So my question is whether like how is it actually better and compared to other clustering methods combined with the lexical search with fingerprints or Tanimoto similarity or stuff like that?
Thanks. The question is how it stand in comparison to clustering just those binary fingerprints, or because it's also possible to cluster them and do a lot of operations, like binary operations on them to achieve similar results. So the answer is yeah, it's possible. It's totally possible to use those binary fingerprints, but with the Tanimoto distance, it's possible possible to do some clustering, but it's much less effective. Those algorithms are not scalable. If you have just a few hundred thousands of those binary codes with Tanimoto similarity, it will take it could take hours to compute the clustering, and then it's still tricky. There are of course there are algorithms for that, but they are not efficient in any way to be comparable with vectors in Euclidean space. The thing is, the question was also whether there is some fundamental difference, because maybe there will be faster algorithms for that. So why is it not possible? One technical detail is the hardware. With dense vector embeddings, you can use all the power of GPUs to make those vector operations and distance computations incredibly efficient. You can, for example, you can compute 100,000 times 100,000 squared similarity comparisons, which is I don't know, it's trillions or more, by doing vector multiplications on GPU, and you will have the result in seconds if you have large enough GPU. But with those codes, it's totally impossible. You would need to do those trillions of computations one by one. You can write efficient algorithms in C++ for it if you want, but the scalability it's just much worse.
Perfect. Yeah, I have two questions as well. I wanted to ask, for example, for some functionalities of the molecules, some of the functional groups might be a little bit more important. So isn't the binary search maybe better in that regard, that we care only about some functional groups and don't care about others, and the semantic search would take everything into consideration? So it might be better for maybe searching for something similar to aspirin, but not something that can solve this particular problem.
The question was if are there cases where the binary codes are better because you have higher control over the features or what the bits are representing. Well, yeah, exactly. There are some cases which are problematic. One of these cases is, for instance, substructure or superstructure search. Because if you are searching substructure of a graph, using some mathematical algorithms for that's like NP incomplete problem. But with binary codes of those features, you can just check if those bits are contained in the bits of another molecule, and as you have those set-based representations of molecules as back of features, you can check if the molecules contain those features you are searching for, thus having much more efficient substructure and superstructure search, which is needed in some cases where you are searching for similar motifs or some smaller molecules or larger molecules with the same scaffold. So yes, there are definitely some cases where it's good to have the control, and this is one of advantages of those binary codes currently over this approach.
Yeah, and the second question was, if you for that use case that you are using this for, do you just suggest the similar molecules and then have the people validate it? Because there are some problems with, for example, chirality. Not sure if I pronounce it correctly in English, but some of the molecules look the same, have the same representation, but have like vastly different effects. For example, like the debacle with the morning sickness pill that causes like severe birth defects, right? Because it was just like the mirror image of it, which is not represented in the SMILES notation, right? So like if you take it into consideration the chirality of the molecules, or it's not your use case.
Yeah, the question is, what about chirality? What about isomers, tautomers, and very similar conformations of the same molecule? So, well, actually, we are hacking this problem in the way that we are searching for all the analogs, all the chiralities, isomers, tautomers. If you want in the search, you can filter them out if you don't want, and you are searching only for different molecules not having like a very close representation.
Thank you.
Thanks. So are there any more questions? Yeah.
Thank you. Thank you for the presentation. And first of all, Miroslav, congratulations for the product. I think it's a very great achievement and seems very promising. I might not have really a question, but rather idea or brainstorm here a little bit. I don't know whether there is anybody who is a pharmacist. Are you? Yeah, that's what I was thinking. Because if I can give a little bit of clinical perspective, there's two topics which are most pressing in terms of new drugs discovery, and that might be cancer. That's more like genetics involved. And then the second thing is antibiotics and bacteria, which are more and more resistant to various antibiotics. And the problem there is that the bacteria figure out how to overcome the biochemical mechanism with which you fight the bacteria with the drug, and they usually come up with totally different way. You use beta-lactam ring as a penicillin, but then they develop beta-lactamase enzyme, and then they can break this antibiotics. So you have to come with totally different antibiotics. And so if I'm thinking discovering just a similar molecule might not do the job, because if there is like specific structure they can fight, it will be in the similar molecule as well. I was thinking if you could, because I very much liked you said you will include also the targets, like you will embed the targets as well. And that's what I was thinking, that if you could embed these biochemical mechanisms of the bacteria and search in them and like find a good path around them, that I think would be very good for the antibiotics. And I think we are having a big problem with the not having enough antibiotics for the bacteria which are resistant right now. So
thanks for this question. We have a question there about antibiotics, where due to some specifics, you cannot just search for the most similar molecule because bacteria are learning to overcome it, and it's of no use there. So currently I presented only the similarity search, where you are searching the most similar molecules. But already you can compute some properties on those vector embeddings with our, it's called cheese modeler, where you are going through the latent space and calculating the properties. You could, for instance, calculate in a very fast way what's the antibiotic resistance probability or what's, for those molecules, and then only filter them based on that. That's one possibility. Another possibility is to stay with similarity search, but employ some techniques of similarity search of molecules which are allowing for so-called scaffold hops or scaffold hops, for instance, are cases where you alter the scaffold or the core of some molecule, and you have similar molecules in the chemical sense, but very different in the graph structure or very different in the graph structure sense. So that's another possibility. And in the shape similarity, we have some, or electrostatic, we have some successes in searching while keeping those interesting scaffold hops. And finally, you asked about what about the targets. For that, you don't need similarity. Well, similarity is useful if you already have some potent molecule and you are searching for similar ones for the target. But you might want to have some complementarity metric. There is a protein pocket or some chemical structure, and you want molecules which are some complementary in some electrostatic way to bind in there, and then you are not searching for similar but for complementary molecule. And fortunately, it's also possible to train a model like this. We are currently doing some experiments, but I will not talk. I would not like to talk about it in details. But you can, of course, learn the AI to not only learn some similarity metric, but also some dissimilarity or complementarity metric, or even to optimize it for diversity to get diverse results. So it's possible. And in general, if you have anything in biology that is possible to capture capture digitally in some like 3D scan or some chemical properties or I don't know, graph, there is always possible to create embeddings for it, and due to the multimodality, you can include it into the search.
Nice. Right, since we are running out of time, maybe one more question online, if there's one. All right, everybody seems to be quiet. So let's thank Mirek again, please.